D of Module 2, Brute Force Method. Part D.1. So let us complete 3 examples left from part C, C.3. Yeah, we have 3 more examples. Yeah. Let's continue from part C.3. Yeah. Question number 7. Yeah. Show that log of n belongs to little o of n to the dth power, but this time d is a positive number greater than 0. We do not require d integer, any positive number. Okay? But here you can see, if you closely look at this, this result, after we prove it, we will use this result a lot. But you can see the only requirement is d positive. If d, how large is d, it's not important. Okay, yeah. So then you can see, even this d is a very, very small number, it is still true. Okay, so let's consider d equal 0.00, I put many 0, 1. Even that small d, it is still correct. So think about that. Okay, all right, so let me prove this first. Little o, when we see little o, most of the time we take the limit, ratio of the 2 functions, then we take the limit. We want to prove the limit is 0. All right, so let's consider the limit. Now, remember, when we take the limit, it is very likely we need to use the L'Hopital's rule. L'Hopital's rule, for that reason, we need to use the continuous variable x. So we change from n to x. All right, so now L'Hopital's rule. So let's take the derivative, numerator, denominator. Oh, before we apply the L'Hopital's rule, let's check if it satisfies the condition. So what's that condition? Indeterminate form. Limit infinity over infinity, indeterminate form. Okay, no problem. When n goes to infinity, the numerator goes to infinity, denominator also goes to infinity. Now, all right, so let us apply L'Hopital's rule. Take the derivative of the numerator 1 over x. Derivative of the denominator, the power rule. Power rule, yeah, d times d to the d minus 1. Yeah, that's simple. Yeah. After simplification, we have 1 over d times x to the dth power. All right? So you can see after simplification, d still positive. Still positive. All right? And this time, it is not an indeterminate form. The numerator is 1, so we cannot use L'Hopital's rule anymore, but we can see the limit immediately. When x goes to infinity, denominator goes to infinity, 1 over infinity, it is 0. So we have the answer, 0. Okay, yeah. After that, then we can go back to the discrete variable m, yeah, because this is the general case. From the general case to the special case. Yeah, so we have, when n goes to infinity, natural log of n over a power function d n to the d, so this limit equals 0. Yeah. That tells us that little expression is correct. Yeah. So that's the question number 7. Yeah. Next, question number 8. Yeah. Show that n factorial. Here, the hardest part is n factorial. N factorial belongs to little o of n to the nth. Yeah. All right. First, we know, take the limit, right? Little o, we need to take the limit. Yeah. But when you take the limit, here, think about another important difficulty. That's n factorial. N factorial. You know the definition of n factorial, right? Yeah, I think everybody knows the definition of n factorial. N times n minus 1, n minus 2, all the way to 1. The product of these n consecutive integers. That's the n factorial. All right. That's the first thing. Second thing, this time if we need to take the limit, yeah, because little o, most likely we need to take the limit, right? Yeah. All right. We want to show this limit equals 0. All right. But now, if we use our old thinking, old method, you will have some pretty big difficulty. So why? Because think about, definitely this is infinity over infinity indeterminate form, right? No problem. The question is, if you want to apply the L'Hopital's rule, you have big problem. L'Hopital's rule. You need to change to continuous variable, right? Continuous variable. But when you change from n to x continuous variable, this n factorial, you will have problem to define x factorial, right? When x is not an integer, how do you define x factorial? Think about that. If x is just positive number, not necessarily integer number, how can you define x factorial? Right? Yeah, so that's first thing. Yeah, it is hard to define, right? Yeah. Second, even if you can define, right? Even if you find some smart way to define x factorial, how do you take the derivative, right? Think about that. How do you take the derivative? It is also very hard, okay? So think about, if we use the L'Hopital's rule, derivatives, we get stuck, all right? Yeah, so we have to find a different way. Yeah. Here, let me introduce a different method. Yeah. Stirling's formula. There is a famous Stirling's formula in calculus. That formula gives us estimate of n factorial. That is the, most useful part for this problem. Now, first, the first version of the estimate is this one, n factorial approximately equal to square root of 2 pi n times parenthesis n over e, e, natural log base, e, 2.71828, many digits after that, to the n, parenthesis to the n. That's the first version of approximate formula. But this one, if we look at this version, there is some problem we're not very happy about. Approximately, this kind of approximation formula is not very convenient to use, right? Not very convenient to use. Yeah. Approximately, so could be larger, could be small, and we don't know if it is larger or small, right? We just know pretty close. It is close, but we don't know, exact behavior of this approximation. Yeah. So that is not convenient. So we want a different version of formula, so we can do better manipulation. Yeah. So the second version will be much better for our purpose. So that is this version. This one, we know larger or small, right? Still n factorial, we have a lower bound approximation, and we have an upper bound approximation. That is very convenient. Okay? We approximate n factorial from both sides, upper side and the lower side. That is very convenient. All right, so now let me show you how to apply that inequality version Stirling formula to find the answer. All right, so let's continue our discussion. This time we use this inequality version Stirling formula. Then you can see after we use this formula, look at our destination expression, n factorial over n to the nth ratio. Look at that destination. From the Stirling formula, we get lower side, upper side expression. Two expressions to approximate our destination ratio. All right, yeah. Then we're pretty close to our goal. We're pretty close. Okay, all right. Now, let's look at the limit. This time, let us look at the limit. When we take the limit, we can take the limit, and when n goes to infinity, when we take the limit, be careful, we need to change less than sign to less than or equal. This one, also less than equal, we need to include that equal case. The reason is simple, because when we take the limit, even if the original inequality is strictly less than, but the limit could be equal. So that's based on our experience from the limit calculation. Let me give a simple example. If you cannot see that fact easily, let me give you a simple example. All right. 0 less than 1 over n, right? This is strictly less than, right? Now, when we take the limit, when n goes to infinity, then this limit equals 0. That's the equal sign, equal to 0. Okay, yeah. So that is pretty obvious. All right, so that's the reason we need to include that equal case, upper, lower, two sides. All right, next, let us calculate this limit, left-hand side limit, right-hand side limit. Calculate that. Okay, all right. We can use our existing result. Yeah, we just calculate similar result before. So let us use it. Yeah, all right. Based on that result, the limit is equals 0. Both sides limit is 0. So let me give you the reference here. Yeah, so the reference is by our example question number 5. We have this. So look at that example. We have that. Okay? Yeah. And we just use d equals 1/2. Yeah. Root of n, right? Root of n, 1/2. Yeah. A equals e. Look at that. A equals the, natural log base. It is greater than 1. Right? So we can use this result directly. Okay? Little o, right? So the both sides, those two limits are 0. Okay? From upper side 0, lower side 0, then our conclusion, the middle limit also 0. Here we use a theorem. Yeah. Some people call squeeze theorem, some people call sandwich theorem. Yeah. You just pick a name you like. Yeah. Squeeze or sandwich theorem. So we get a solution. We get a proof. All right? Yeah. So think about that. So for this question, you can see we need to use a key result, Stirling formula. Then the squeeze theorem, sandwich theorem. Yeah. So try to understand. Yeah. So this is a, you need some special knowledge here. Yeah. All right. Now, the last question, number 9. This one, multiple choice question. So we have 5 small options, small, little questions. Yeah. So let's look at one by one. Yeah. So we want to, for the following given functions, so we want to indicate the class big theta of g of n, the function belongs to, each function belongs to. Okay, yeah. But for the g of n, we want to use the simplest g of n to represent big theta notation. Yeah. All right. The first one, a, this function. Yeah. Second one, square root, so this function. Yeah. C, this one. Okay. Yeah. D, exponent, but sum of 2 exponent functions, base 2, base 3. Yeah. E, the last one, floor function of log base 2 of n. All right, yeah. So let's work one by one. Yeah. The first one, yeah, it is not very hard. So first one, we drop that +1. We only keep the n squared because that's the dominant term. We only take the dominant term, n squared. The n squared omit +1 term. So n squared then to the 10th power. So n to the 20th. Yeah. So we get a big theta of n to the 20th. Yeah. B. Similar to the first one, we only take the dominant term. We drop the minor terms. 2 minor terms. We don't need to consider. Yeah. The reason we already in our discussion analysis. So we talk about that. So we can comfortably draw these 2 minor terms. So we take 10 n squared. Yeah. But 10 is constant, right? 10 is constant. We can even drop that 10 constant. So we just take n squared. N squared root, that's n. So the answer is big theta of n. Big theta of n. Yeah. Very simple. Yeah. Next one. Yeah. I want to look at E first because that is the easiest. Yeah. The hardest I want to leave to the end. Yeah. E, floor function first. Floor function, we know it's an approximation, right? We drop the fractional part. the fractional part is very small, less than 1, right? So we don't worry about that less than 1 difference. Yeah. So first, we drop that floor function. So we have the log base 2 of n, right? The log base 2, the base, here when we consider big theta, the base number is not really important. Yeah, the reason I can explain, after you get all the answers, I will explain a little bit. The base actually is not really important. Yeah. But here in our textbook, if we omit, we just use LG, omit the base by default. In our textbook, it's base 2. Yeah. But in math textbook, it will be base 10. Yeah. The default, LG version log. In math, it will be base 10, but in computer science textbooks, base 2. Yeah. But as I said before, that base 2 or 10 really not important. Not important. Yeah. We will see that because the difference is just a constant difference. The constant difference for our asymptotic notation, it's not important. Okay? Yeah. All right. Next one, D subproblem, D dominant term. These two terms, one dominates the other one. So base 3 exponential function dominates base 2 exponential function. Yeah. You can understand easily, right? If you cannot see, you take the ratio. You take the ratio, then take the limit. You will see the limit is 0. Okay? The ratio 2 to the n plus 1 and 3 to the n minus 1. All right? Even plus 1, minus 1, just constant, right? Yeah. 10, n plus 1, can you write 2 times 2 to the n, right? Minus 1, can you write it as 3 to the n divided by 3, right? Yeah. So finally, you only need to consider this ratio. When you consider this ratio, its limit is 0. So base 3 exponential function dominates base 2 exponential function. So that's the reason we just take the second term here. Then our big theta, g of n function, we choose 3 to the nth. So that's D. Yeah. Finally, the last question. Yeah, so that's a little more complicated, so I leave it to the end. Yeah. We have 2 terms, so we need to compare these two terms. Which one is dominant? So we take the dominant term. Yeah. All right. So let's look at log. Yeah. So that part. Yeah. Log of n plus 2 squared. Yeah. By the property of logarithm, this exponent 2 can be brought down here. So constant 2 times log of n plus 2. Okay, that plus 2 can be dropped, right? Yeah, that plus 2 can be dropped. Okay, yeah. So constant 2 times log of n. Okay, yeah. All right, so look at the log part of the second term, this one, by the property of logarithm. Yeah, we can write log of n minus 1. Yeah, here we assume the base 2, right? Yeah, minus 1, base 2. Yeah, minus 1, this minor term can be dropped, right? So the key part log of n, the key part also log of n, right? Yeah. So the log part in the two terms, they are the same. They are the in the view of growth function, they are the same, right? So we only need to compare the non-log part. Clearly, the second term dominates the first term. Yeah. So for that reason, we should take the second term. When we take the second term, we drop the constant. Plus 2, we can drop it. Okay? Yeah. So at the end, we get the simplest g function, big theta of n squared times log of n. Log of n. All right. All right. So we finish all these these 5 small questions. But at the end, let me explain one last thing I mentioned a little bit. The change of base rule in log, change of base rule. Why the base here not important, right? Yeah, I mentioned why the base, which base we use in the big theta or asymptotic notation for log is not important because we have the change of base formula. Yeah. So suppose you have base A, you can replace, use this formula, you change to base C, different base. All right? Different base, you can see log base C of A, that will be just a constant. That will be a constant, okay, after you change the base. So the difference between 2 base expression, just constant factor. But for our asymptotic notation, constant factor does not change the order of growth, right? Constant multiple does not change the order of growth. Yeah. So based on that, so we don't worry about what base it is used, but we only need that base A greater than 1. That's important. Base A greater than 1. Yeah. All right. So I finished all the 9 examples for part C. So let us finish our D.1 video right here.